Welcome to my YouTube channel. In this video, we are going to learn how to calculate the nuclear spin, the parity, and the nuclear magnetic moment of a nucleus. Now, unlike the atomic model where we have filling of orbitals, the s, the p, the d orbitals, we also use that same idea in shell model to study the nucleus. Okay, but the difference between that of the atom and the nucleus is that the way you feel the orbitals in the nucleus is different from that of the atoms. So the pattern that we are going to be using is given below. We fill this one first, followed by this, followed by this, followed by this. You can see this particular pattern in some textbooks, right? Some standard nuclear physics textbooks. Okay, so we must follow this pattern, this order. It goes from this point. When you get here, you continue from this point down to this point. You get to this place, you continue from here down to this place. Although it still continues, but we just limited it up to this point. Okay, the maximum number of electrons this one can take is J, because this expression represents J, 2 times J plus 1. This expression is J multiplied by 2. Then add 1 to it. That will be the maximum number of nucleons that this particular one can take. Okay, so the maximum number of protons and neutrons in each shell is given by 2J plus 1. Now for 1s, we have 2 times half. This is our half, which represents J, plus 1 equal to 2. So that's how you feel it. Now for parity, we use this formula, minus 1 LP plus Ln. This one represents the L from the proton, the L from the neutron. These are quantum numbers from the nucleus. First of all, we must note that LP or Ln is gotten from this value 0, 1, 2, 3, 4, 5. So if your neutron or proton falls on the s orbital, you give LP 0. If it falls on P, you give LP 1. If it falls on D, you give it 2, so on and so forth. LP is the remaining unpaired proton. Ln is the remaining unpaired neutron. Okay, so what we have is the LP remaining unpaired proton and Ln representing the unpaired neutron. Okay, so if the unpaired proton is equal to 0, then the parity will take this from minus 1, 0 plus Ln. But if Ln is equal to 0, which means all this one represents even number of neutrons, then we have parity equal to LP plus 1. But if you have your Ln equal to LP equal to 0, which signifies or which implies that there are no unpaired electron, unpaired neutron and protons, then the parity equal to what? 1. If you have one unpaired neutron, one unpaired proton, which is equal to 1, then the parity is equal to what? 1. So if the parity is 1, then the parity is even. If it is equal to minus 1, then the parity is odd. When we talk about parity, we talk about wave functions, right? So the position of the neutrons and protons, they can be found in the positive coordinates. What if you now send them to the negative? You now find them in the negative coordinates. Will the wave function still remain the same? That's what we mean by parity is even and parity is odd. So when parity is odd, it means that the wave function will no longer be the same. If it is 1, that means the wave function will be the same, irrespective of whether you change the position from positive to negative. Okay, so for even nuclei, right? Even nuclei, which means no unpaired neutron or proton, then what we have is that our J will be equal to 0, our parity will be equal to 1. We've seen it from the previous slide, right? Okay, for odd even or even odd nuclei, J is decided by the last unpaired nucleon. So if you have odd proton, even neutron, right? Then our J will be decided by this odd proton. If this one is even proton, odd neutron, then our J will be decided by the odd neutron. For odd nuclei, if Jp, for us to calculate J, if Jp equal, if there are J plus Jn plus this is odd, then we use this particular formula. Like, if not, we use, if the addition of all this is even, then J is equal to this expression. Okay, to calculate the nuclear magnetic moment, we use this formula for this. So let's say that after finding out if our Z is odd or number of neutrons is odd, we need to carry out this calculation. We already know what our L is, which is coming from SPDF, right? To know if it is 0. So once you know your value of L, you add it to half. If it is equal to the calculated nuclear spin, then you use this particular one, any one of these two. But if not, if L minus half is equal to the calculated nuclear magnetic spin, then use this one for odd Z or this for odd N. So let's look at a typical example. Find the nuclear spin, parity, and nuclear magnetic moment of carbon-13. So carbon-13 has 6 protons and 7 neutrons, right? Now, since N has 1 unpaired nucleon, we won't use this one anymore. It is this one we'll now focus on. So filling the shells, we have, this one can take a maximum of 2 neutrons, 4 neutrons, 2 neutrons. So since we have 7, you fill this one and fill this one will be 6. The last neutron will occupy this one. And because if it is occupying this one, we can now say that the nuclear spin is what? Half. The nuclear spin is what? Half, because it falls on this. The 7th neutron falls on this. So the nuclear spin is what? Half. Then this is P. Our L will now be what? 1, because S is 0, P is 1. So Ln is equal to 1, Lp is equal to 0. Nothing falls there. So our parity will be equal to minus 1, Lp plus Ln. What is our Lp? 0. What is our Ln? 1. Why is it 1? Because P is equal to 1, S equal to 0, D equal to 2. So P equal to 1. So we use 1 equal to this one. Okay, so we have now the nuclear magnetic moment. Since N is odd and J equal to half from our calculation, using this one or this, let's say, since we know that our L equal to 1, if I put 1 here, 1 plus half will give me 3 over 2, which does not match this. If I put 1 here, 1 minus half will give me half, which matches this one. So I'm going to use this expression, which we brought out in our previous slide. Okay, so if you notice, we are going to be using this one, and since this one is odd proton, odd neutron, we are going to be using this expression because we have agreed that our L minus half is equal to half, so it falls under this category, which is under this. So 1.93 J all over J plus 1 mu N. Okay, so that's why we'll now say we are going to use this expression. This expression is now this. Our half, J here is half, all over half plus 1. By the time you simplify everything, you get this particular expression. So that's how to basically calculate the nuclear spin, parity, and the nuclear magnetic moment of a nucleus. I hope this helps. Thank you. Share and subscribe.